Hello my friends, welcome again to my video channel. Today we will finalize the project with the high voltage power supply. First we will do some tests regarding overload and short circuit, whether the power supply survives a short circuit at 400 volt output. It has to survive it, otherwise the specification is not fulfilled. We will do also some optical works regarding labeling on the pots, switches, also on the meters and on the scale. Let's start. But first some final modifications and improvements in the circuit. In the last video sequence I told you that I had some problems with the overload protection, which is not always working as expected. I think I found the reason. First I tried to change these resistors, but this was not the problem. I thought there is too much load on the output of this op amp. This was not the problem. The problem is the voltage drop over the Zener diode. In the first versions I had only 4.7 volt, which was too low, because when you have here an overload and the voltage here rises, then this output goes up, and due to the low voltage drop here, the cathode of the optocoupler is energized very fast, and the output current is shut down before the op amp goes into self-hold with high output, because we have a 7.5 volt, and when we have a trigger at 5.5 or 6 volt, which is sufficient to trigger this transistor, then 6 volt is not sufficient to hold the plus over the 7.5 volt. So I increased the Zener voltage version with 8.2 volt, and now the problem is solved and we have stability. This is still 1K and still 10K, only an increased Zener voltage here. This forces the op amp to increase the output voltage up to more than 8.5 or 9 volt. And with 9 volt the transistors are triggered. The LED indication, of course, but also the optocoupler to shut down the output voltage. But when we have here 9 volts, then it is sufficient to keep the positive input above 7.5 volt, which was not possible with 4.7. This capacitor here also plays a role. It is delayed, so it delayed the self holding function. Okay, this is solved. In the high voltage supply itself, I only swapped this 100K, it was 100 not 10K, this is wrong, 100K, it was a series of two resistors, 47K. There is sometimes a high voltage drop protected by the Zener diode when we have a short circuit here, 400 volt DC output, and then we have a short. This capacitor is charged up to nearly 400 volt, and this would cause here a negative voltage swing down to minus 400 volt. The FET is protected with this Zener diode, but the resistor here would have a high voltage drop about 400 volt, and some resistors are not specified for such high voltages. A resistor is not only specified regarding power or thermal dissipation, it's also specified regarding voltage. And some, especially smaller resistors, only have 300 or 400 volt nominal. So two resistors in series are always better. That's the reason why I also have chosen here two resistors in series, not only one. Second one, this bleeder resistor here is not necessary, because we have another bleeder circuit, 4K7, and the pot for the negative output, and here back this also has 100K, so we don't need here another 100K. And the second circuit is via this resistor, and this resistor to the Zener diode, which has 12 volt. So this capacitor is always rapidly discharged down to 12 volt via this path, 10K and 15K. So we don't need a bleeder resistor here. This is also deleted. And now to the labeling. I printed on a self-adhesive white foil for laser printers. It is not transparent, it is white, as you see. Some text, some labels, which I will put onto the front panel as we have here, this is a switch for the meter B plus measurement or C minus measurement. And this is the option to measure with 300 volt full scale or 600 volt full scale. We have 400 volt maximum output. Here we have some smaller text. I will put it onto the scale internally with milliamp maximum indication. And these are for the switches and plugs, fuses on the rear side. So first I will add these labels. They are not protected against deleting the text or so. I do not add another foil on it. It's just for demonstration purpose. This is only a provisional construction here. It's not for the final solution. I only do this to test it and to see whether the concept is right or wrong. I hope it's right. So the labels are not for permanent indication. I don't even know whether they are ultraviolet proof or so. I think they will yellow out over the years. But for the next month, that's okay. The labels are added. Setting for B plus and C minus up to minus 120, 25 or so volt. The meter settings, reset function B plus, B minus ground, C minus output. This is related to the common. Here we have two separate windings for 6.3 volt filament or heater supply. They can be added in series. We'll discuss this later. On the rear side, the fuses are installed and labeled. This is a primary fuse for the line side, and these are the two fuses for the filament for the heaters. And now I will start with the meter. For this purpose it's necessary to take out the bezel and then to take out the scale. Removing the bezel is rather easy. Simply two screws have to be removed, stay here. And they need to be collected. And then this one. And now it depends of course on the type of instrument. We have here two another screws which hold the movement and the scale. They can also be carefully unscrewed, taken out. And then this one. Okay, it's a little bit difficult, but it's okay now. First will become the milliamp meter. We have 100 milliamps, 200, and the maximum indication. And additionally, where is it? Here is it. I will replace the volt by milliamp. The instruments are labeled. So the milliamp meter maximum 200 and some milliamps. The 300 is covered, it's not valid. On the volt scale we have three scales, 200, 400, 600, depending upon the setting of the switch, or 100, 200, 300 plus, and the negative, the C minus, minus 50, 100, minus 150. So it's ready now and we can do some tests. Now some checks of the accuracy. First the B plus. The meter is set to measurement of B plus. Scale is 300 volt. It's 100, 200, 300. When I go to 100, the instrument has a little bit of non-linearity. 200, it's more accurate, and 300, then it is okay. It's non-linear, this one also. go to 600. That means 300 is exactly in the center, and 400 volt DC output here is okay. 398. It's smaller than the error in the pointer, so this is okay. Now let's check the C minus output. I go with the meter to C minus, negative, minus 50, 100, 150. So at minus 50, is it minus, yeah, okay, minus 100. Okay, and minus 120, that's the maximum. 119, that's also okay. This voltage, of course, is very weak, and even the instrument, the load of the instrument is too high for it. So when the instrument is switched from C minus measurement to B plus, then there has to be an artificial load to compensate for the change of the impedance. And we can see when I have, for example, minus 100, and when I switch the instrument to B plus, this voltage does not change. This is done by a special arrangement of the switch, which replaces the instrument by a short circuit to ground. We have a series impedance of 150 kilo ohms. The instrument itself has only 230 ohms, so we have 150k, and there's the option when I switch to B plus, and the 150k, the series impedance, is connected to ground. So the C minus source sees again 150k ohm to ground. So it is a constant load, and the output voltage, sorry, I'm B plus here. The output voltage does not vary when switching between B plus and C minus. Now we check the accuracy of the milliammeter. I've added a series resistor. It's 100 ohm in series. Meter is set to 300 B plus 300 volts. That's okay. And that means we have 100 milliamps at 10 volt. This is, by the way, the worst case for this power supply, because the power transistors are heavily loaded. A big voltage drop, 400 volts across the transistors. And when I go to 200 milliamps, okay, a little bit of parallax error. And the maximum, when I go to the maximum, we will see the overcurrent protection, overload. That's it. Then we make a reset. Okay, works also. Calibration seems to be okay. 100 milliamps. Could improve it a little bit. 202, it's okay. It is not necessary, because these instruments are not very precise. They have specified class 2.5. So this is not a precision instrument. It only costs some euros per unit. It's not worth to discuss it. If you need a more accurate metering, use external digital multimeters. And now to the two filament outputs. Each of the outputs voltage is reduced to 0, set to 6.3 volt. Okay. Operator too stupid error. We have 6.79. It's a little bit more, because this voltage is given for a load at 2 amps. And this one, the second voltage, also has a little bit more, 6.8. When we load it, it will go down. And now, a small speciality, the two phases of the two voltages, they are potential free, independent windings, completely isolated. They have opposite phase direction. This one, for example, goes in this direction, the upper one in the other direction. So I can add it simply by using a short plug like this. And then from here to here we have gas. Should be 12.6, a little bit more, 13.5. We can also, of course, shorten it on this side. And then we have the output here. That's also possible. But when we add it in the wrong way, just a nice experiment, for example, from here to here, there's a voltage we added, but then we will measure from here to here. The voltage is nearly zero. So that's the problem when adding AC voltages, the phase is decisive. But here we have the advantage that we can easily add the voltages, or we can use them separate, completely isolated. For example, to use one with a bridge rectifier or so, and the other one for direct heating or any other purposes. So I decided to use 4 connectors and not only 3. 3 would be possible to have here one winding, here the other winding, and a common point, the center tap, but I decided to have 2 separate AC filament windings. Now we have here the test of the voltage stability by changing the load. There is a maximum load, 2 kilo ohm. This would mean at 400 volt, 200 milliamps. We see 600 volt. We have here, okay, that's the limit, 395. Here we have some problems because this is the limit of the power transformer, and when I reduce now the load, I plug it off, you see the voltage arises, goes up and goes down. So this is not typical for the voltage stabilization. Let's go down to 380, 385, 82, 360. Here we see the stability gets better when we go down in the voltage. This is expected because there's more overhead in the voltage regulation when the output voltage is a little bit lower. And now we go down in the load. We have 1 kilo ohm load. So we can check the lower voltage ranges. I go to 300 volt. At 100 volt we have 100 milliamps. 96, 97 something. This is a good stability. Here we go to the maximum current at 200 volt. 198, 199, 200. A variation of 1.4 volt. I think this is also okay. And now I will choose another load. It's getting nicely warm. It's cold outside. This could be a okay. Got some heat. Now we have 100 ohm as load, not 1 kilo ohm, so we can check it at the very low output voltages. I'm setting 200 milliamps. This is 19 volt. And when I unplug the load, 21, 19.7, I think this is okay. So in general, the voltage stability is rather good. It is not perfect, of course. We have only one transistor in the voltage regulator in the amplifier circuit in the loop. So could be improved with a higher gain. For example, with a differential amplifier or so. But this would maybe cause again stabilization, voltage, oscillation problems. Stability against oscillations could decrease. And now we will check the output voltage regarding variation of the AC line. Here we have the measurement of the line voltage. The moment is 230 volts. This is a DC output voltage. Again, I have full load 2 kilo ohm. I set the voltage, output voltage, to not exactly 400, a little bit too high. Let's go to 374, and then I vary the AC voltage. And you see, it is rather stable. So I think there's no big change in the output voltage with varying line voltage. This is acceptable. Oh yeah, the resistors get really hot. The measurement of the output ripple and noise is done with this little adapter. It's a homemade, 20 years ago. It's more or less only a coupling capacitor inside, up to 2 kV, and an overvoltage protection also, so the maximum voltage is 60 volt peak, which is possible. Frequency range is, I think, starting with 10 or 20 hertz up to some 100 hertz or kilohertz in the range. It's especially made for ripple control. We have full load. Sorry, need it here. We have here 100 millivolt per division, increasing the output voltage up to, we are 200 volt now. We see there's a small ripple. Current is 100 milliamps. The ripple is in the range of 50 millivolt peak or less. With increasing voltage, of course, the ripple increases a little bit. And here, when we come into the region of the limit of the power transformer, the ripple increases, and then suddenly we have some stability problems. Okay, that's the limit. We see more noise. Okay, this is due to the a little bit weak power transformer, but the ripple is still in the range of 100 millivolt peak with full load at full voltage. And when I go down to a lower voltage, again I use my 100 ohm resistor. Oh really, they're really hot. Next time I use a cup of coffee and place it onto it. Then I have a hot coffee in my workshop. Then I go into the range of 10 volt output voltage, 20 volt, again only 50 volt peak, 50 millivolt peak, also very low. But this is the worst case for the operation, because we have the maximum heat dissipation in the output transistors. Now again, overcurrent protection, and then switched off. Okay, the ripple is acceptable, no other noise on it, only the absolute limit on the power transformer, the maximum of the power transformer. There is some problem, but again, this is not the problem of the electronic, that's the problem of the power transformer. And now the master of all tests, the short circuit test with full output voltage. The negative lead is connected to the ground, to the chassis of this experimental board. The resistors are not active. I increase the voltage to 400 volt output, maximum voltage, and now see what happens. Reset, try it again. You see a short pulse, but not more. The ammeter didn't observe the ammeter, makes a short jump. So this over voltage or over current protection is very, very fast, very rapid, and it protects the instrument, the power supply, and also the load very well, and I think it is fast enough. I will try to measure the time with a shunt and with my scope or so. I think about the circuit. And after some short circuit tests, as you have seen in the last footage, I suddenly had no output voltage. I thought, oh no, not again, killed transistors, but the transistors were okay. The problem were the series resistors in the emitter. In the emitters of the 4 power transistors, I had 4 resistors, each 100 ohm, these types, and they were killed. That cannot be. They have 3 watt, a short current pulse, the continuous power is 100 or 200 milliwatt, and a short current pulse of 2-3 amp shouldn't be too much. It's not the current, it's the voltage. You can see this resistor when I make the picture a little bit bigger. Maybe you see here this small dot above the 1 of the 100. There's a small spot, and the other resistors looked similar. And then I had a look into the data sheet. I should have done it earlier. And the data sheet showed me, even for very, very short times in the range of microseconds, not milliseconds, microseconds, the maximum power is not more than 300 or 400 watt. I thought, okay, 400 watt, but then calculate 4 amps through a resistor of 100 ohms. That is 4 square is 16, it's 1600, it's 1600 watts peak. Short time, of course, the electrolytics are discharged, but this is a short moment where the voltage is, the voltage across the resistor is too high, and so the resistor is killed with the voltage drop across the metal film. It's a film inside the metal film, and this metal film is killed by overvoltage, not by heat. So I decided to use other resistors, and I found some types which are much better, and I added 2 resistors in series. I show it. You can see it, metal film resistors, but they are specified for 30 watt. The first ones only had 3 watts. 30 watt each, 50 ohms, so totally 100 ohms. They are in series. Each has 30 watts, but more important, each resistor has, according to the data sheet, a short time voltage of 500 volts across the leads. 500 volts, 2 in series, so I have a maximum voltage of 1 kV. This is far beyond the maximum voltage of the electrolytic caps, which is 700 or 800 volt, cannot be charged higher. So these resistors are good enough for the purpose, and they are limiting the current. So these big resistors here are good. They are much expensive than the first ones, and I totally have 8. I have 4 in parallel and 2 in series. Each has 50 ohms. The white side is for cooling. I don't need any cooling because the heat is not the problem. It's only the current pulse. And now I will do a short circuit test again and measure the current. The test circuit now is a little bit more sophisticated. The output of the power supply plus minus 400 volt is potential free. We have here a shunt. This is the ground, the reference for the scope and also for the trigger pulse. And here we have the power Mosfet, an external power Mosfet, which is triggered with a single pulse from a pulse generator, 5 volt peak or 10 volt peak, sufficient to trigger the transistor. And then when the transistor is triggered, conductive, then the 400 volt shorted via this path here. So we have nearly a total short circuit for a duration of half a second or so, not important. I will set it to a long time. I use a generator because a manual triggering with probe or a tip or so is not okay. There's contact bouncing, and this is not a constant pulse. I need a constant pulse. The shunt 1 ohm is connected to the scope 10 by 1, and I show you the setup. Here is the setup. So this is the output of the power supply. It is potential free. The ground here is only used to ground the test board. Here behind the positive lead, it is switched off, no fear. Here we have the transistor, and this contact here is a drain connection, as we have here, plus pole. The minus pole is connected to this shunt, which is grounded, and over the shunt there is a probe 10 by 1. It's fed to the scope, and here I have a pulse generator set to single shot. Duration is maximum, it's some 100 milliseconds. So it's good for a single shot. It's good enough for this purpose. Set to 5 volt. Output peak. By the way, the cable is terminated here with 50 ohms at the input. The output voltage is 400 volt, set to maximum voltage, but that is not so relevant because short circuit current is not specified, where the voltage is specified by the internal capacities. But anyhow, 400 volt, and when I trigger the pulse generator, then have a look at the LED and the scope. Maybe you have heard it, the variac also makes a small sound. And now we can focus on the picture of the scope. We have here 500 millivolt times 10, 5 volt per division, so we have a 10 volt. Shunt is 1 ohm, so we have a peak current of 10 amps for a certain time, and this is now the discharge curve of the filter capacitors in the power supply on the rectifier side. And here after we have 2 milliseconds per division, 2, 4, 6, 8, 10, 12, 14, 15. After 15 milliseconds, 15 milliseconds, the current is switched off internally by the automatic overcurrent protection. This current here, constant current, I assume it's generated by the power transformer and rectifier diodes. This is approximately 5 amp continuous current. We have heard in the variac some current flowing, so I think this is the short circuit current of the variac. Okay, that's a proof that the overcurrent short circuit protection operates. Now I will reduce the output voltage down to 50 volt. 100 volt. I set it here to, let's go to 300 volt. Go down to 100 volt. Reset the scope. Single shot. A little bit strange, the picture. The mains fuse was blown. Maybe too many short circuit tries. It's 800 milliamp medium low. Not fast, it's only medium, but maybe the summation of the short circuits. I try it again. I have 100 volt. Same again. Why is this fuse always blown? The reason is the primary fuse was blown. It's a fuse on the line side. 800 milliamps, medium blow. I have a new fuse in it. Maybe the old fuse got a little bit too much tries, short circuit tries, and therefore the fuse was damaged, pre-damaged, preloaded. So I have it again. We have 300 volt, 100 volt. Now a lower setting. Scope is set to single shot again. And now let's have a look at it. Okay. We have a little bit of different current, but again 10, maybe 15 amps. I really don't understand what this is. Maybe the voltage stabilization tries to hold the voltage and increases the output. So we have a step here which is not present when we have 400 volt, because there is no overhead for the voltage regulation. So this may cause an additional step. Okay, but in general the most important thing is that the short circuit control operates. Maybe I have to readjust the fuse, different characteristic. But the most important thing is what we have seen, that the output current here, it takes a little bit more time now to switch off. But it works. We have seen the LED. Okay. After some successful short circuit tests, we are at the end of this project. The prototype is ready, is working. It still needs some minor optimization. It's not perfect. Some ideas I have will be included in the final design, but I think I don't show it in detail in the videos. That makes no sense to show you all minor steps. The result, of course, will be shown here on this channel. And now at the preliminary end of this project, one personal note. Please do not send me emails and ask when the PCB is ready. You will be informed on this channel and on my website. You will find the link below when it is ready. I will try to produce a professional PCB together with my friend, which you will most probably be able to buy. But of course you will get the full schematic and some layout hints, so you can do it also on a perf board, on the experimental board. You are not forced to buy any PCB from me if you don't want. My channel is not commercial, it's only a hobby, and when I can sell some PCBs I will be happy. It will be good for a cup of coffee or so, not more. But again, I do not know when it is ready and when it is available for you. Again, do not ask me. I cannot say it, and when it is ready you will see it. That's the end of this project. I will have some minor works, but to you, stay tuned, stay healthy. See you on this channel.